notes for 10.5 and 10.6, we're going to start off using the ideal gas law. That's from 10.4, the ideal gas law, which is PV equals nRT. But we're going to use it now in like a derivation or like a derivative. We're going to use it and take a look at what we did here. It says if we divide both sides of the ideal gas equation by V and by RT, we end up getting N over V equals P over RT. Now that works for us because what we're going to do is we're going to look at density, and we know what density is. Density is equal to mass divided by volume. Okay, so if density equals mass divided by volume, notice that we have a volume here and we have a number of moles. So the number of moles is, well, here I'll show you what it looks like when we continue on with this. Remember that number of moles times molecular mass equals mass. So that's like saying I have 1 mole times 16 grams per mole, and that means the moles cancel, and what I'm left with then is just 16 grams. Of course, I used oxygen's molar mass for that. We're talking about 1 mole of oxygen. So there's where I get my mass from, but when I plug this into the equation, I have to, first of all, we end up with something that is like number of moles, because number of moles is on top, okay, equals mass divided by molecular mass. And they use a capital M here, but I use an MM for molecular mass or molar mass. And when I plug this in here, I get mass on top, and then I notice that I have to multiply both sides by molar mass to get it to go to the top, which is why it ends up here. So in short, what I'm getting to is that density is simply equal to pressure times molar mass divided by RT. R is a constant, so for the density of a gas, all I need is the molar mass, or the formula, pressure and temperature. And that's it. We're going to use this. We've done an example problem already, 10.A, 10A problem set number 48, I believe it was. If you need to go back and check that one, it's the beginning of part 2 for 10A problems. So there's mass divided by volume equals density. So mass divided by volume equals pressure times molecular mass divided by RT. And then it says, note only one only needs to know the molecular mass, the pressure, and the temperature to calculate the density of a gas. What about molecular mass then? Well, if D equals PM divided by RT, and we solve for M, then I would be dividing by, I would multiply by RT, right, to get rid of that, and I'd divide by P. So that's what we get here. Density times R times T divided by P is molar mass. So we can always find the molar mass of a gas given the density of it, the temperature, and the pressure. Now we're going to take a step into something a little bit different. Pretty soon you're going to do sample exercise 10.12, and 10.12 has to do with collecting gas over water. This is why Dalton's law of partial pressure is important. If we have like air, the pressure of air, okay, now air has a whole bunch of different gases, but the 3 main gases though, actually the 2 main gases that makes up 99.9% of all the gas in air, and then there's a whole bunch of other stuff, would be the pressure of nitrogen plus the pressure of oxygen. If you add those 2 together, you get basically the pressure of air. This would be Dalton's law of partial pressure. So you can basically add pressures of gases together to get a total. That's just, with air, that's just one example. You would also, if you wanted to be really finicky, you could also include water vapor and, of course, a certain amount of carbon dioxide. And then we get into, like, of course, the pressure. There's some noble gases in there, like argon, and there's a whole bunch of other stuff. But that's if you wanted to get really, really, really picky about it. So in other words, basically whatever the total is equals whatever the gases add up to be. Could that be any easier? Probably not. So here's where we use that. This is directly related to 10. Here's the same graphic that we use for 10.12. It says when one collects a gas over water, there is water vapor mixed in with the gas. So you notice the tube here. The tube here should be filled with nothing but O2 because that's what, this is the KClO3, and when you're heating it, it yields to give KCl, which is not a gas, plus O2. And then it's this O2 here that follows the tube and then starts to populate. You can see it bubbling here up, and then it's only O2 here, except for the fact that water evaporates. We all know that water evaporates, and it evaporates depending on the temperature, only the temperature. So we can find out exactly how much pressure water vapor provides or is part of the total gas that's being collected at the top of the beaker. Maybe I should say at the bottom of the beaker because this is a beaker that's flipped over on the bottom. Okay, so anyway, it says to find the pressure of the desired gas, one must subtract the vapor pressure of water from the total pressure. And that kind of looks like this, where P total equals the pressure of whatever gas we're looking for plus the pressure of water vapor. Okay, now there's obviously, if we're looking for this gas, it would be very easy just to flip that around and go P gas equals P total minus P water. And that's what our working equation typically is right there. So we're going to subtract the total from the water vapor, or the water vapor from the total. And that's it. Good. Kinetic molecular theory is 10.7.